Okay, cool. So the next one would be basically a workshop that will involve Jupyter Notebook and will cover some basic stuff for image recognition. So there are three ways of doing that now. Basically, if you got Python installed, you got your laptop ready and set to go, you can go to this link here. I can, yes. This link. That's the repo with the Jupyter Notebook itself. There's requirements, files, etc., etc. All you need to do to get you started with the workshop. That's one solution. But if you don't want to do it this way, we prepared some online environments that will not require some installation. That's basically almost the same link. That's without the underscore repo. This will send you to the, how is it called? Google Colab. But the disadvantage of that is that it doesn't really display the images that good. Like the zoom feature is missing from Jupyter Notebook in the Google one, so it would be be harder to see the results. But they are there basically. You would be able to finish the workshop. There are a couple of exercises, and yeah. If you're ready, still let me know if there are any problems with installation. Also, let me know. Sure. That's the Google Colab, and the other is basically the same with just underscore repo. No. Yeah, underscore repo. Yeah. Just clone it and run it. Any problems with installation, maybe? Yep, just let us know. One-on-one. How's it doing, Chris? Sure. Okay, sure. So we'll start. So basically, what we are trying to achieve now is to get to know basic image processing methods from OpenCV. Then we will go to the feature matching, feature detection, feature matching, and then in the end, we will try like custom solution for the matching multiple images in the target image, which is not really there out of the box in OpenCV. So we'll just play around with that. So if you're using the Google one, you got some cells, some more cells than it's here. Basically, what it does is just downloads all the resources that are needed for the talk. So just go ahead. To run a cell, it's just shift and enter. It will tell you, yeah, that's really bad because what was that? It's this the one. It's perfect. So you go here to the first cell, click here, shift enter. There it is. It's running.
Maybe you can show it up on the presentation.
Yeah, I think so. Because most of the guys are doing that. What's that? Okay. Oh, yeah, sure. I don't even got this one because that's mine. So yeah, somewhere here is the open in playground button. Just click it and it will ask you if you want to run it, etc. Just say yes. It's fine. There's no viruses there. Or are they? Yeah, exactly. It's running. Yeah, it's initializing. Yeah, it's perfect. So we try with exactly. So run anyway. Yes, restart all resources. Yeah, it takes time because it's connecting to the initializing. Sure, connected. It's running. What it does is basically just downloads the resources that we'll use later. Which takes time. Sure. The next one is just installing the requirements for our project. Yeah, fancy. Mm-hmm. Exactly, just tell us. Something is wrong, just tell us. Mm-hmm. It takes time, of course. Or if you got Windows, just don't use today's presentation, basically. Yeah, we got some issues with the Windows also. On the link, it's fine. It would be okay. Doesn't really matter. Exactly. So if it's if it's up and running, that's the first test. Is it okay? Yes. Okay. So just this third one should be okay without errors. That says that we're good to go. So basically, what we're doing here, after we download all the resources and install packages, we're just importing all the modules that we're using. Here, we're specifying, just please run it as I go. We're specifying all the paths for the files that we're being using. Here are just some helper methods for displaying images, and the first one, it's this one. So what we are achieving here is just using OpenCV to load image of this young fella in color, basically. we specify it here. That's the flag for OpenCV to just load the image in color. Here, sure. If we print the shape, that's the shape of the NumPy array that the image is where image is stored. And what does it mean basically? So if we load the image to the computer, we need to somehow store the data. The file itself is just bytes, of course, but to make a computation or just process the images, here we need to store it somehow. And OpenCV uses just NumPy array, and basically this one here is just 3D array. This one is how many pixels are in, how high is the image? That's the width of an image, and that's mysterious 3 here. That's the 3D, yeah, like the depth of the image. And what does it say? So for each pixel, for each point in the image, we store 3 values, which are from 0 to 255, which together combined will tell us what is the color of the pixel. So if we try to run this one and see what's stored in the first pixel, it means that it's some mysterious 62, then 78, and 104. You need to, this one is just BGR, because OpenCV stores the colors in this format, meaning that it's not our beloved RGB. Is there BGR online? Maybe it is. No, it's not, of course. RGB online. Yeah, and what does it say? We got some values here, right? So it's reversed. So red is 104, green is 78, 8, and 62. Exactly. So that's the color of our first pixel with this left top corner here. And that's how the images will be represented later. Okay, so the first exercise would be to basically reuse the code from this cell and play around with different constants. Just use for example the reduced color too, and see what happens, etc., etc. So just play around with that. You can also, one thing is that you can also use this one, which is another display image grayscale image. Yeah, that's what I named it. So if you input the image in grayscale, you'll use the flag here, for example, the grayscale one. Just please use the display grayscale image, because there are some issues with the otherwise. So basically, your code goes here. Basically, just please load the same one. Just use this command, emread. Use the same image path because we want to load the greg, and then just change the flag and display an image. Yeah, you should. No, just select one. But the grayscale would be interesting. And that's the effect for the grayscale. We just said that CV, that's this one should be interpreted as the grayscale image. But if we check what's there for our first pixel, that's 83. And what's the shape? Input image. That shape. Perfect. So we now know that the array is now two-dimensional. Basically, we just store one value for every pixel in the image, and basically to represent grayscale, it's just one value from 0 to 255. And this one, the value we got here, just tells us how bright or dark the pixel we are trying to get the value of is, basically. That's the first one. That's the first exercise. Just basic uploading images or loading them into to operate with OpenCV of them. So what we are going to do next is simple image processing, and basically we need to see what we can do with images in OpenCV. So here I got some real quick code snippet, and it's not that it's not loaded. It's basically what we did. I used the blur methods or function from the OpenCV module that will basically do this one. This one, like the FI, like the results you will get, it's it's based on the value here, which is kernel. And the exercise 2 would be just to play around with the values there. You get two values, they don't need to be really equal. Just play around with those and see what are different results and how shape of the kernel, put it like that, will affect the result image. Issues? You're the owner, remember that. Not everyone, but I think it can affect mine. Yep. So, yeah, sure. What's happening? Oh yeah, exactly, because that's the thing. That was the issue with the displaying the image. So if you change it to grayscale, grayscale image, and run it again, how is it even called? That's how it is. Grayscale. Yeah, there it is. Cool. That's the previous one. So yeah, I just changed the kernel to be 50 by 50, and that's the result we got. It's more blurred than it was. If we change it to something like that, we see that the kernel is not square anymore. So the blur is kind of, it goes to the sides, and that's how you can operate and play around with different effects just by changing two values and see what happens. So that was blurring. That was basic image processing. So now the next one would be edge detection, or using such a function that will emphasize the edges and that are placed in the image. So this snippet here, run it. Yeah, that's the same Greg. Like it looks in reality what we got from the function, which is called Laplacian. That's what we got, which is not really visible there. That's why I enhanced it for a better result, and that's what we got. The algorithm, what the function does, is that the algorithm just detects it where the edge is, and it's emphasized. We can display that, and we know that's that's the shape of Greg's head. There's a nose here, there are ears, etc., etc. You even know that I enhanced this one. That's why we can see even the beard, basically. Yes, that's why. Because the algorithm just saw that it's something there, like the line. So it was emphasized. So yeah, but we used Laplacian. That's one of the approaches, but we got different ones in OpenCV, and the next one is that's the exercise 3. Just use the Sobel one. That's the syntax for it. You need to play around with key size parameter. And you just need to remember that the key size needs to be, odd number from -1 to 31. Basically, that's just the requirement for the function. So just please run it. You'll run it on different image. That's just some Sudoku picture, like picture of the Sudoku puzzle. You put it in grayscale, and here you need to run the Sobel on that and display it. -1 is, so if it's not -1, it's just basically size of a kernel for Sobel function. If it's -1, it's special kernel of size 3 by 3 with really good results. That's why I put it there, because that's the best. That would be the best solution here. It's just special number they put there. Yeah, in the Sobel one. Yes. Because they optimize it somehow. They use specific kernel. Yeah, that's a lot of math involved there. But yeah, that's why I chose this one. Okay, so run it. Yeah, you can see. You can also display this one first. What's the original image? And it's this one. That's just photo of Sudoku puzzle. And here we run Sobel on it to detect the images, the edges, sorry. And if we run it, we can see that the lines and the numbers were enhanced, and that we can simply tell, where the boxes of the Sudoku puzzle ends. We can use it later, for example, to solve the puzzle. By running some algorithm, just by looking like inputting the image of a puzzle. That's possible. That's how it is. But we can also get back to the Laplacian one and see how is it with Laplacian. Okay, let's do it like that. Laplacian image, Sudoku image. Is it? Is it? Okay, so that's the effect of Laplacian. Yeah, it's really hard to see there, but you know, you get your computers, it would be better then. So the edge detection, that would be the first step to our feature matching or feature detection. So what is the feature of an image? That would be the question. So basically it would be a point in an image that will be really characteristic for this image, basically, that will allow us to find it in other images, and that will yeah, help us get to know where the image is in the other image, like where the common, you know, common features or common areas of the image are in two different images. So to start with image, you know, recognition or, you know, matching, we need to discover the key points. So today we'll be using the SIFT algorithm. Of course, there's some cell for the ORB, but mostly we'll use SIFT algorithm, which would be, you know, most famous, to be honest. And what we are doing here, yes, is running some magic from OpenCV. Here we specify that we or instantiate the SIFT algorithm, and then here we create key points from SIFT detect, which will basically run like on the image we got. We'll try to find the most characteristic points in that image. Here we're just drawing the points. So what would be the characteristic point in an image? Basically, most likely corners, because that's how like the easiest thing to detect, the corners. So that's what we mostly see here. For example, there are some key points here in the corner of the lip. There are a lot of points here in the corner of the eyes. Even there's a key point here when the hair of the Greg ends. There are some key points in where the ear is really characteristic. So the data here would just allow us later to match two images. That's different algorithm here. That's ORB. You can see that found key points are different. For example, there's no key points here, and not sure what that is. But the pattern here, the ORB is not really matching this one, but the SIFT, there's a lot of those here. Okay, so exercise 4. I would like you to use the draw key points function for the same Greg image, and just change the flag to one of the others, most likely to the draw rich key points. Just that would be, that will show us something later. Yeah, there was a question? Not really. Yeah, okay. Okay, so why it didn't, So basically, I change it. Okay, so the question was why the Sobel function didn't detect the horizontal lines, the horizontal borders. That's actually brilliant to spot. So what it does when Sobel is run, it's run for specific direction, vertical or horizontal. So if you change this one around, yes, that will tell us what are the horizontal images, borders or edges. So yeah, so to get full idea or full picture, where are the edges, you need to run Sobel with different one. Yes, yes, basically. But that's brilliant. Cool. Okay, get back to Greg. So what changed? Basically, now there are this really big circles displayed, and that's just Sift telling us the size of the circle is basically how large is neighborhood of specific key point, which is here in the middle, that was taken to compute descriptor. Descriptor is basically, yes, the description of the neighborhood, like what is surrounding, what are the surroundings of specific key points that will help us later to match key points in different images. And this line here or here would just tell us what is the direction of the key point. Here is just the key point on the chin is just facing up because the chin is facing up here. The lip here is, you know, it's there, so that's why the direction is there, etc., etc. That's how it is, and that will this information also help us to match the images later. Okay, so we need to start, you know, feature matching. Here in the so to you know, to start feature matching, we need to have some, you know, two images basically. The first one is still our beloved Greg, and the other one is just memes funny image. Display image, memes funny image. And memes funny is basically a screenshot of the website where our beloved Greg is. It's this, of course, it's the same image, but here the Greg itself is cropped, and here is in full size. And our goal would be to know or have computer tell us that Greg is here on this image. That's our end goal. So let's just move that. What we're trying to achieve here is just loading to images, you know, instantiate the Sift algorithm, detect and compute. That's the function for like detecting the key points and computing the descriptors, which we got here. We need to do it for both images. Okay, so what we need to do now, no, not need to do, but that's the exercise. Just please display the memes funny image with the like the key points drawn on it, like we did before, basically. Yes, yes, exactly. Sure, it's good. Out image is nothing, yes. And key points are memes funny key points. Image is, and let's see what it is. Yeah, it's there, but it's really, really small. That's why. It is, because we are detecting key points for whole image. So the characteristic points of the image with the memes funny screenshot are, there's a lot of them. It's not only the Greg, of course, because we're not yet matching the two images. We don't have the data about the other one. So basically, we are just, you know, looking for the points, the pixels that will be, you know, characteristic for the memes funny image. That's why there's a lot of them, because the image itself is bigger than Greg. That's you know, that would be one thing. So yeah, if you displayed that, we can tell, or not really, because the image quality is really bad. But if you see closely, I can see that there are key points here in the, you know, in the corner of the lip of the Greg. There's this key point here, you know, from the hair. You know, also there's a lot of key points here in the eyes. So we know that we know that we found the key points that will be, you know, it would be easy to match in our procedure, in our algorithm, because, you know, they're the same. They have the same qualities, the same descriptors, etc., or similar descriptors, to be honest. Okay, go back here. Let's just proceed. So if you got key points and descriptors, we need to have some algorithm to match those. Basically, we instantiate the BF matcher. Not, you know, go into details. Let's do basically, but we'll just straight away run the matching function. So we pass the descriptors and descriptors for both Greg and memes funny, and we retrieve the first match. And the match itself, the object has attributes like distance, query ID, and strain ID. So the distance is the comparison of the descriptors for the two key points we found, basically. So the lower the value of the distance, the better the match is. The less they, you know, differentiate between them, it's better. That's the better match, basically. They're more likely to be the same, basically. That the match is good. And the query ID and tray ID is just IDs of key points in both images. So yeah, that's the key points here. Like the match here, this match consists of key point with index 0 from Greg and key point of index 4000, yeah, etc. from memes funny. That's how it is. It would be, you know, used later. Okay, so now we want to display the matches, just what we got here. Okay, here first I sorted them by the distance. The lower the distance, you know, the better the match is, and I displayed only just 10 of them. So it's hard to see, sure, of course it is, but if you look closely, we know that for example, the neck key point from the Greg, that's you know, mini Greg here, was matched with the you know, neck key point here, etc. The same for the lip, and that's the drill. That's how we found some similarities between the two images. Okay, so we will use the information basically to get to know where the Greg is. Basically, we'll just go to it later, but for now we will use another matcher which would be this one is the matcher that will take into consideration the nearest neighbor. So you select the key point and then you look for the closest one. So here, just I want you to compare the values of distance for both matches, the main one and the nearest neighbor, basically. And we will, you know, tell something about it in a minute. So that's the output of prints. So it says that, the distance, which would be the quality value of the main match is 59 and the other one is 300 something. So it means that the first one is a lot better than the other one, basically. That's what it says. And that's the thing to remember. And then we go to the loss ratio tests. So when I don't know, professor, I don't know, the guy that created the SIFT algorithm, in his paper decided that we will run the k nearest neighbors matching, which will have the data of the neighbor's distance, etc. And based on this data, we will decide if specific match is good or not. In his paper, he set the value to 0.8 or 0.75, doesn't really matter. And we are using this test here and in this cell. So basically, that's the empty list for good matches, and for every match, we test whether the distance or the ratio of the distances between the neighboring matches are to the below certain ratio, basically. And then if we run this one, sure, okay. And now that these are the matches. That's basically because here before we just displayed 10 matches, and now we are displaying all matches that are good, depending on the ratio test. That's the value for the ratio. Okay, yeah, and here we just drawing KNN matches, basically. So this task, this exercise would be just to play around the distance, not the distance, the low ratio, and see what happens. How does that affect how many matches we got in the result picture? Okay, so if you put the low ratio to 1, that's basically, all the matches would be displayed. And we'll lower it to, I don't know, to 0.1. Nothing is left. So yeah, doesn't really, matter. Or 0.2, actually, this one was good. Yeah, and this will lower the number of matches significantly. So what does that tell you about the ratio test? Why does it exclude some of the matches? So basically, if the ratio or the distances for both matches, the main match and the neighbor match, would be quite the same, we're not really certain that it's a good match. That's not really a characteristic point for this image, because if there's points in image that have similar features to this one, that says that that's not a characteristic point, basically. So it will not ease the process of image matching. That's why we exclude the matches at certain point, basically. And the low ratio, you know, the value was just trial and error, basically, and some tests that were, you know, performed during the work on the paper for the SIFT algorithm. So we'll get back to the 0.8, 0.8, doesn't really matter. Just please correct this because we are using the good matches again and run the cell, of course. Okay, or 75, doesn't really matter. So if we got matches, we got key points. Now we got matches, we discard the bad matches. Basically, what's left to do is just to tell where the Greg is in memes funny screenshot, basically. And what we will do, what we will use, would be the finding the homography for this image based on the key points for both images. So if you see it that way, based on the distances, not the distances as a value between, you know, of descriptors, etc. The distance, the physical distance between pixels in an image, basically, that would be you know, example here. So based on the knowledge that, for example, this key point and this key point, there's a certain pixel distance between them, and that those two has different you know, distance between them, because, you know, the Greg image is smaller, or it's not, or the other information is that this key point is placed on the, you know, more right, you know, compared to the whole image. And this one, it's kind of in the middle because that's only Greg's head. So based only on this information, we can, with some certainty, assume that the Greg image in memes funny image is here. And that's what we use the find homography function for. That's what it does, basically. It's kind of converts one image space to the other based on the information, you know, not correlation, but the placement of different key points in both images, basically. That's what it. Sure. Yeah. Yeah. Mm-hmm. That's from video, or that's live in, like, placed in a car? Because in the car would be just most likely sensor that will, you know, measure the distance. But you mean a video? Sure. Yeah. It's just seeing where the bumper is in front of you. You know, from the video, you can tell what's the distance. Sure. Of course. But that's another thing. It's just, you know, of course, that's another thing. Machine learning is not. It's, yeah, exactly. Yeah, that's the you know, image recognition, you know, 201. Yes. Okay. Yeah, that's basically it. You can tell a lot from, you know, distances and placement of an image. That's what we're trying to achieve here. Exactly. 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 Where's the line on the road, etc., etc. Of course, basically. So we will use this. There's a lot of magic here. We just retrieve the points that are for specific matches, blah 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 blah, etc. Find homography, and this one would be just placing the. Cool. So now, based on the matches here, we know that the Greg image is here, which is actually, yeah, that's the true, because the Greg is limited. It's kind of, cut out. And that's where the Greg is, basically. That's the algorithm that told us what is the border, basically. What would be the border, or where would be the Greg cut out from the memes funny image. And you need to also remember that it doesn't really matter if the Greg in target image is bigger than it was in the source image, or maybe Greg would be, reversed, whatever, etc. That's the SIFT algorithm, scale invariant, feature. Feature. Yeah, exactly. So that's how it is. I don't have examples for that. Just that's easier to show basically here, but it doesn't really matter if it's scaled or it's it's rotated. So we found the Greg. That's cool. Just to play around a bit with this one, and I would like you to change the color of the border to red. And just remember that we are in the BGR, color scheme, because that's SIFT, and that's what I did. There's some comments that will help you achieve that, but basically there's this Polylines function that will draw the borders for us based on the points we retrieved from the perspective transform before. Actually, it's here. Draw a border in green color. Just change it. Just change on the existing one. Just get to know the code, and that's there. Is there? Yeah, there is. Sure. Okay. So we know the Greg is there, but we would like to display the image also, the matches also. Okay, so we now know quality is really bad, but what can you do? That's limitations of the collab environment. Okay, so we using this snippets. We again draw matches. We give the points. That's the homography image was the image with the border. That's why we got both the border and the matches. Okay. So now what I would like you to do is play around with the matches mask parameter. There's exercise listed here. Just please change it to this one and see what happens. Of course, rerun the cell into draw it. Okay. So what we achieved just by changing the matches mask parameter for the draw matches function. Basically, what it does is just that it will display every 10th match that we got in our collection. Basically, the matches mask is a list of zeros and ones that will tell us if we should draw the match or not. And we should draw the match only when the match is in liner with the specific area that is selected by the borders. We kind of cheated because the matches mask originally comes from the find homography one. It will tell us that, for example, this match doesn't really fit in the matched area that we will achieve here. Okay, sure. Okay, yeah. So the matched mask would be a list of zeros and ones. If for specific index in the list there's a one, the match of the same index we got in our matches will be displayed. If there's a zero, the specific match will not be displayed. And it's just only we kind of play around with manually, but it comes from the find homography. Entire match. Yes, that's how it is here. So here, so we put it that way. So there's one for only for those for every 10th match, right? So here we can tell that we drew fewer matches, right? Excuse me. Exactly. If we go back to the matches mask, which that's what's come from the find homography. Yeah. So basically, in this case, I think every entry in the matches mask list is one, basically because in this case, actually, every match was inliner in the area that we matched. That's just lucky strike, basically. Okay, cool. If we got this one, that's the final part of it, would be multi-matching, basically. Because in the case we got now is Greg and Memes Funny, there's only one Greg in the Memes Funny image. So we'll try to match different image, but with multiple source images in the target image. Here I just instantiate the flan matcher. I will skip talking about that. We'll just use it later in multi-matching. So multi-matching is not really given out of the box in OpenCV. So we need to come up with different idea for that. Basically, what it's used here is the mean shift algorithm, which will cluster or group key points depending on how close they are to each other. That's the basic idea. So if we got specific cluster of key points, like the group of key points, which is you get multiple of them as a result of the mean shift algorithm. We're kind of dividing the target image. That's the image we are looking for specific, for specific picture. We're dividing it to couple of areas, basically, and then we were just running sift algorithm and matching later, flan matching in this case, for every area, for every fragment of the target image, basically. That's how we achieve multi-matching. Okay, so we are loading different images that will, which takes time. There's sift compute already done for us. There's some computations that are required for the by the algorithm itself. Doesn't really matter. And here we are just running the mean shift. Mean shift takes one parameter, which is named bandwidth, and here we are running some function from scikit-learn to kind of estimate based on our data set what would be the best parameter for mean shift in this case. So we're just running that. There are some parameters you can adjust, but for now we just run the min shift. Sure, we divided our key points based on their placement in the picture to groups. And here, for every group, we are running the matching, basically. That's what it was before. We are retrieving matches, we're discarding the bad ones, etc. We're grouping the matches to display them. Okay, just run this one, sure. And then for every cluster, we're doing the same what we done before. It's just basically homography and getting to know where the meshed area is. Just run it. That's the same how it is. Of course, yeah, sure, that would be painful. Yeah, that's what I'm doing. Sure, should be. Sure. Should be okay now. Sift. Give me some sift. Give me a sift. Where is the sift? Sift is here. Just take the sift. Instantiate sift. Sure. We're running the detect and compute. Okay. We're dividing it. Clustering. Flan-based matcher. Okay. Flan. Okay. Go. Sure. So if we zoom in here, one important thing. What is actually, it's too large, basically, doesn't really matter. Okay, so we got this. No. Wait. Code. Go. Okay. So we got this big screenshot. There are multiple of those lion logos. The other one that was matched is here, for example. But there are a lot of logos here that weren't matched. And why? So basically, to match all of them, we would need to play around with this one, and just do it. I suggest you lower the value of this one, and at certain point you'll get all of them. Just play around with that. I'm not sure if that would be visible on the Google environment, but I will just I'll take you there. Okay, that's half. Need to run the sure. So basically, you need to start from here. Just upload the image. Yeah, exactly. Okay, we changed it to 0.05. There it is. And we kind of improved because we now are matching those two also. There they are. But still, those are missing. Okay. Excuse me? Yeah, we should go even smaller. And the correct answer is, no. We should start, wait. Yeah, here. There it is. That's the correct answer, because these are matched. These are matched. These are matched. This one is matched, but those here, actually, they are not. But it wasn't really possible to match them because they're too small, basically. And that's one of the problems we're facing, dealing with image recognition, that it's really, really hard to match really small images. We as humans, we know that's this one, right? Even if they're not really, good quality, etc. We see the colors, we see the shapes, etc. It's obvious for us, but for computer, it's really, really hard to match them, basically. And it wasn't really possible with the setup we got now. Okay, cool. So that would be an introduction to image matching, image recognition, image processing. A lot of stuff was here. The link would be there for you to play around. Just it would be perfectly fine just to to upload your images and run the SIFT and then SIFT algorithm and then flan matching, for example, just to play around and see what results you can get. Thank you very much for listening. Question?
Anyone wants to talk about something? Cool. Piotr again.
Thank you.